Hello everyone, it's been a while since the LiveEye project has begun. My part was about making a new solution targeting materials optimization of lightweight gear transmission components. Throughout this journey, I was focusing on reducing the weight of the gears, proposing a new design of hybrid metal composite gears. The innovative design was initially validated numerically. Then the steel carbon fiber gears are manufactured and tested on a test rig provided by Vibratech company. The outcomes were remarkable. A 50% mass reduction was achieved compared to conventional gears while maintaining or even surpassing their NVH performances. This breakthrough demonstrates significant potential for lightweighting in gear transmission systems. By the way, I encourage you to dive deeper into our findings by checking out the published papers linked in the description below and visiting our website. Finally, as the LiveEye project is coming to an end, I would like to thank you all for your support throughout this journey, which was full of energy, interactions, commitment, and integrity. Also, I would like to express my gratitude to all the LiveEye beneficiaries and partners for their support, and especially to Marie Curie program, which gave the existence of this opportunity.
Hello, my name is Feras Bejar. I'm the ESR number 2 of the LiveEye European project, focusing on the design of lightweight transmission systems. 2 years ago, I posted this video on social media where I talked in more details about the strategy I'm willing to undergo to reduce the weight of the gears. As you can see, this can be achieved by removing a fraction of the material and form a pattern of holes. The question is, which pattern configuration guarantees the best compromise of static and dynamic characteristics of the gearbox? To test this, first it is essential to build a dynamic gearbox model which has the most essential components being the power loads, gears, shafts, bearings, and the housing, and this will allow us to test different designs and assess the sensitivity of the response to variations in the pattern distribution parameters. So to summarize the simulation process, we start by doing a contact analysis to determine the excitation by transmission error. We decompose the signal into its individual harmonics, and we use them to excite our system at the meshing region, and then we track the evolution of the dynamic response for each of these harmonics and across the frequency range. To generate the different patterns, we've built an automatic gear blank pattern randomizer, which is a CAD integrated application that relies on the macro geometry details of the gears to generate all this kind of bizarre configurations. And this will be used in conjunction with a PSO-based pattern optimization algorithm, where we start by generating an initial population of designs. We inject them into the dynamic model, we update the model, we calculate the different responses and the fitness function, which takes data from the amplitude and frequency of the mesh harmonics and the sidebands. And then from these population, we select the designs that minimize the fitness function, and we use their pattern distribution parameters in order to orient the generation for the upcoming iterations. We repeat this process several times until the convergence criteria is met. This is an example of some of the outputs which depend on how we tailor our objective function, whether we focus on the reduction of the maximum amplitude or on shifting the resonance peaks. We can get all kinds of scenarios adapted to different loading conditions.
The main objective of the LiveEye project was to reduce the weight of gearbox transmissions. My research focused on the lightening of the housing, which is a component that protects and supports all the gear arrangements within the gearbox. There are two main ways of reducing the mass of a component. The first way is by optimizing its geometry. For that, I use topology optimization methods. And the second way is by using materials that are by essence composites to manufacture. However, when we reduce the mass of a component, we might have problems of vibration and noise emission, And to mitigate those, I consider the introduction of vibroacoustic metamaterials in the housing to mitigate them. It was demonstrated that these passive low-cost solutions might offer a promising solution, a promising technology to allow the manufacture of lightweight housings and eventually the production of lightweight EV motor housings, allowing then the more eco-friendly mobility solutions for the future.
Hi, I'm Siddharth Dave, a PhD researcher at TU Darmstadt and a part of the LiveEye project. Transmission systems are highly dynamic in nature, and any attempts in reducing their weight to enhance vehicle performance leads to increased noise and vibration behavior. This becomes especially challenging for electric vehicles since increased vibrations become more apparent to the user due to reduced masking by the absent combustion engine. However, electric vehicles have a trick up their sleeve. The traction motor present in the powertrain can be used as an actuator to counter the vibrations. By measuring the vibrations through strategically positioned sensors, additional counter vibrations can be introduced in the system through controlled torque ripples. These torque ripples can cancel out the unwanted vibrations. Such an approach does not require any additional actuators, making it economical and easy to integrate. To investigate this solution, an existing test rig at the Institute for Mechatronic Systems has been modified to accommodate a single-stage gear train. The test rig consists of an eddy current-based load machine and an asynchronous electric motor. Additionally, high-resolution torque and speed sensors at the input and output let us evaluate the state and torsional behavior of the system. The single-stage gear train, on the other hand, acts as the test unit. Accelerometers mounted on the test unit housing are used to track the vibration behavior of the system and implement the active vibration control strategy. The strategically placed accelerometers pick up vibration signals from the housing. The source of these vibrations is the gear mesh and its fluctuating mesh stiffness. The vibrations generated at the gear mesh reach the housing through the shaft and bearings and are eventually radiated by the housing in the form of gear whine noise and structure bond vibration. By processing these signals using a control system, control torque ripples are introduced using the drive motor to cancel out these vibrations. However, certain challenges need to be overcome to make such a system practical. This includes the efficiency of the motor and the supporting power electronics, which can take an impact when such a system is implemented. These effects are currently being investigated as part of this project.
Hi, I'm Ranim Najib, ESR5 at the LiveEye project. My PhD is carried out under the supervision of University of Naples Federico and Vibratech. In this video, I'm presenting my research outcomes where I successfully address different research gaps and introduce both computational and experimental innovations in the field. My work has focused on achieving optimal NVH in transmission systems, considering the inherent complexities arising from various parameters and mainly affecting the static transmission error. Why does this matter? Well, it's not just about ensuring quiet operations. There's a significant industrial need to tackle the inherent uncertainties in transmission systems while keeping computational costs in check. The main target is to develop fast and reliable predictive tools that address uncertainties in transmission systems. So, what are these uncertainties? Our exploration has led us to identify the sources of uncertainties, including manufacturing tolerances, voluntary profile corrections, assembly errors, and uncertainties arising from measurement process affecting gear's transmission response. Sensitivity analysis based on the Morris method is carried out to select the optimization parameters and rank the effect of manufacturing uncertainties, considering a broad range of operating conditions and geometric dispersions. The effect of uncertainties is highlighted through detailed experimental investigations involving both static and dynamic measurements. Extensive experiments were conducted measuring 6 per gear pair and 4 helical gear pair configurations, where significant differences were detected in gears with the same macro geometry but different profile uncertainties, and the resulting mesh excitations led to notable fluctuations in dynamic response. These experiments are finally compared with a numerical computational scheme, providing robust predictions of gear response even in the presence of deviations.
Hi, my name is Barbara, and as part of the LiveEye project, I carried out a research on lightweight transmission design through multi-objective optimization and digital twins. The main goal of the LiveEye project is to develop a gear transmission that can have a compromise between lightweight design and also good performance in noise, vibration, and harshness. To achieve this, we can perform a multi-objective optimization, but this is a very complex task that can be time prohibitive. To overcome this challenge, we explored the use of digital twins. Digital twins are virtual replicas of physical counterparts constructed using physics and database models to provide fast and informed decision-making decisions. We implemented a machine learning-based digital twin, focusing in the challenges related to its implementation in the vibroacoustic domain, namely the limitation of machine learning in modeling non-smooth functions, also its lack of interpretability, and the need of large amount of data for machine learning models. To address these challenges, we propose a digital twin framework that integrates neural network models with physics-guided features to improve accuracy and physical consistency, and that also incorporates sensitivity analysis to improve interpretability and reduce the problem dimensionality. Furthermore, we propose a novel application of transfer learning to transfer the information from the previous generation of the product to the current generation of the product. Like this, we can enhance data efficiency and enable the use of machine learning under data scarcity. We evaluate the performance and applicability of the proposed digital twin framework in a real study case for gear transmission design. In this case, we transfer the information from a combustion gear transmission to its hybrid version using transfer learning, which allowed us to reduce the prediction error of the digital twin by more than half. Furthermore, we apply this digital twin in the optimization of the gear transmission, leading to a reduction in the mass, but also in the source of the noise. Furthermore, this optimization took only around 2 minutes, and it would normally take some months, showing the relevance of the proposal digital twin in vibroacoustic design.
Hi everyone, I'm Sina, originally from Iran. I worked with LiveEye Consortium as an earlier stage researcher. My research topic entitled Semi-Active Vibration Control Approaches. It was a fantastic opportunity for me to split my research activities between academia and industry. In Warsaw, Poland, I worked with Adaptronica company, a research and development center which major focus was on smart technologies. There I learned a lot about sensors, actuators, mechatronics, test rig development, vibration measurement, and so on. I designed a semi-active isolator in Adaptronica. In this design, I utilized metal rubber, a material that can be tuned by compression to dampen vibrations in a wide range of frequencies. For the compression aspect, I received a research promoting gift from T-Motion company. By conducting several assessment tests, the isolator I designed turned out to be quite effective in cancelling vibrations in mechanical transmission systems. Later on, at the University of Naples Federico II in Italy, I continued my research activity I used the same semi-active isolator to cancel noise and vibrations in a fiat transmission. I ran the control using Raspberry Pi 4 microcomputer, which its high processing capability has made it useful in a wide range of applications, from weather forecasts to space projects. The remarkable features of this compact gadget, including small size, lightweight design, alongside with the energy efficient characteristic of the semi-active scheme, can meaningfully contribute to reduce carbon emissions in the automotive sector. Throughout this journey, I participated in various Live Eye events. In these events, I was able to showcase my work, receive feedback from experts, and attend useful workshops in NVH, transmission, lightweight structures, mechatronics, and so on. In some Live I program has been an incredible opportunity for me to learn and grow in different working environments. I appreciate the Live I consortium, which brought together the academia and industry and all associated experts who contributed to this project.
Hello, my name is Sneha Rupa and I'm ESR number 8 in the project LIVI, working on developing active vibration control systems for gearbox housing. The main motivation of developing such a system is the enhanced push in the automotive industry towards innovating lower emission cars. And as a consequence, the transmission is one of the main targets for lightweighting components. The active vibration control system is designed to control the increased vibrations as a consequence of this lightweight. The vibration dealt here is the gear whine, which is then transmitted to the car frame via multiple mounting points. The core principle of an active vibration control system is to synthesize an isolating signal via smartly integrated piezo actuators. The main features answering the main scientific questions is to develop an active vibration control system that is robust at high frequencies, typically up to 5 kHz. The actuators need to be smartly integrated so that we use minimal number of actuators, thus leading to an economical add-on solution. As a first step, alternate sensors are looked for. We need to capture the dynamic behavior of the transmission up to 5 kHz. Traditional accelerometers have limited bandwidth up to 3 to 8 kHz and are also rather expensive. We also need sensors that do not alter the dynamics of the transmission because of their extra weight, which is why microfiber composites have been chosen for this job. After this, the force requirements for an actuator are established. The actuators are then need to be appropriately placed so that the vibration at multiple mounting points can be minimized with minimal number of actuators. More actuators means more cost to the system. Hence, an optimization of the layout is necessary. To bring everything together, an onboard controller was needed. Since the vibrations occurring here are high frequency, a high speed yet economical microcontroller such as the TeamZ board was used to put together the onboard controller. Finally, the established procedure was applied to a real hybridized transmission to check the effectiveness of the developed solutions. The work performed as a part of this research was published in high-impact conferences. In the end, I would like to thank Horizon 2020 and Marie Curie Actions for funding this research. Also, last but not the least, I would like to thank my supervisors at TU Darmstadt and PowerFlex for their unending support and feedback throughout this project. Thank you.
Hello everyone, my name is Sharif Okta and I am ESR number 9 in the LiveEye project. Within the LiveEye project, I worked on the development of an active vibration control system for gearboxes. Within the project, I had mainly 3 goals. The first goal was to develop highly integrated and economic actuators for the active vibration control system. The second goal was to design and build a proof of concept test rig for validation. And finally, my final goal was to design a powerful, efficient, and economic power amplifier for automotive application. So first I started by developing an inertial mass actuator that includes a piezoelectric stack, and I used piezoelectrics because they are efficient at high frequencies. That designed actuator was compact and also lightweight. Then I traveled to our industrial partner Palflex in Italy, and there I designed and built the test rig to validate the developed active vibration control system. And we can see here that the developed test rig had a gearbox that had a simplified gear train, and also it had the non-rotating elements. And on the right, we can see the excitation system that was used to excite the gearbox. After that, I tested the developed actuator on the gearbox in cooperation with ESR number 8, who developed the sensors and the controller required for the active vibration control system. And the system worked successfully, and we can see right a significant amount of vibration reduction within our targeted frequency range. Then I developed an enhanced version of the actuator, which had two shear piezo shear actuators and an inertial mass. This actuator had several advantages. For instance, it's lighter and more compact in size. Also, it has and the actuators have lesser capacitances, thus they consume much lesser energy. And finally, it can operate in 2 modes to target the high frequency mode shapes. And this concept has been validated on a simple plate setup that's shown on the right. And we can see also a significant amount of vibration reduction using the new integrated actuator. Finally, I also developed a switching amplifier to power the actuators. And you can see here the developed amplifier being tested. And on the right, we can see the control signal in yellow and the output signal in blue going to the amplifier. And it had the required voltage and currents that were required by the piezo actuator. So that sums up what I did in the LiveEye project, and thank you.